the session from now, and I'm gonna share you my screen. Do you see my screen now?
Yep.
Good. So for this week, I know the chapter 10 do have a lot of content. I time to time said to you all, the textbook author use chapter 10, 11, 12, 13 for a next class, for their next class. So not only one class, they for two classes divided. So this is given in a second class. But just to get a heads up, what it's covered in the chapter 10, that's what we're gonna do today. At the same time, I will send out a course evaluation survey as soon as we complete this session. It's a anonymous URL, anonymous course evaluation, so no one will see who's doing who's recording what, and I will not get an access to the records until your grades being finalized. So feel free to complete it and let me know your feedback, any uh, text feedback, your personal feedback about any comments on the online part of the program and the face-to-face part of the program. That's very much useful for the future. Keep that in mind. So as you see it here, there are like 10 videos that related to this chapter that we need to go through in one session. Don't worry, because many of you have completed 239. So some content that you covered in 239 is very much helpful in this class or this chapter. So if we go back to our original design, do you remember that this 7? Okay, someone is waiting. Okay, add that. Why it is not going out? Okay, minimize. If you remember our 7-layer architecture, so now logic gate comes into the bottommost level. Logic gate comes into the bottommost level. So with your C programming, with your assembly programming, with your do you see my face in the screen? No. Oh, I didn't start my video. Sorry for that. You see me now?
Yep, we can see you.
Okay. So in the past, so we went through these levels. So now in the bottom level, I remember I said all these calculation happen at the logic level. So ultimately it's a logic program that's going to do all the additions, all the subtraction, all the division. So how that happened in the logic level is what we're going to discuss in this chapter. To better understand that, we need certain things, how the logic programming works, how the truth tables work, how the logic being represented in logic tables, and how the binary numbers being sent to those logic gates. So micro level, logic gate level, then you will have the electronic device level. So once you put it into a logic gate level, then it is going to be 1-0 instruction for the electronic device that's going to function according to that. So keep in mind, we have about 112 slides to go through, but I'll try my best to making it sure that you know what required for the exam. Even though this chapter is pretty long, in your exam, only gonna question the truth table and the logical expressions. Logical expression, I give you the guarantee. So I will making it sure that the questions that come from your come for your exam from this chapter is only from that content. So combinational circuit can be anything like this. You may have certain inputs coming in your way and you generate outputs. If you remember our accumulator and the index registry, you receive numbers, 16 of them, 16 digits, and you do certain calculation and restore it. Remember that, right? So in some instruction, you take some values from the memory and do a function, apply a functionality at the index registry or the accumulator, and store it back either to store index registry or accumulator. In some instructions, you don't take any memory address or location, but you apply a application for what in the index registry or accumulator? Can someone tell me what are those instruction called as? Anyone? No?
Can you say the question again?
So instruction that happen within the index registry or accumulator, what are those instruction called as?
Like the calls to get them from the memory?
No, not instruction that do not use any memory. Unary, right? Unary
Oh
instructions.
yeah.
Examples will be shifting to the left, to the right. You know, remember those instructions? Shifting, the binary addition, binary. Sorry, shifting to the left and right. And when we do the division and when we do the multiplication, we use those, right? So how this happen inside our circuit is what we're gonna figure out in this chapter. So in truth table, if you remember the truth table, if you have a two inputs, so you can easily decide what's the output are. If you have only two inputs, you can easily decide what the output are. I'm sure that you're familiar with some tables for the and the OR gates. You know, we can come back to that in a minute. But if you have more than two inputs, if you remember our accumulator and the index registry architecture, it has 16 digits. You take another value from another registry, also 16 digits. Now you have two 16 digits lines sitting next to each other. You start adding those numbers from the right, then you add those two numbers and store it back, and then you go to the next one. Then there will be sometimes there will be a carry forward, right? If you had 1 and 1, there will be 1 taken to the next level. So we have to accommodate third digit as well. You get what I mean? So if you only have a two numbers, that's gonna not bring any carry forward. Yes, you're fine. But if there is any number that need to be carried forward to the next level, you need to accommodate that. So therefore, most of the time in our architecture, at least 3 digits will be appeared. 3 digits will be appeared. So what we need to pay it can be more than 3 sometimes. You know, it can be 4 or maybe 5. So better understand that you need to have a basic knowledge of Boolean algebra, how it's worked, the binaries, OR and AND gates, and some algebra theorems. We call those in these names. I am not expecting anybody to remember the names, but those theorems or those concepts. If you remember this is called as a cumulative theorem. So as you see it here, the x plus y is equivalent to y plus x. There's nothing wrong with that, right? So I know this even been taught in my math syllabus in high school. This was taught in grade 8, says universal mathematical theorem. So x plus y is always equivalent to y plus x, and x multiply y always equivalent to y plus y multiply x. So there are a few of those associative theorem. So when you have x plus y plus z, then that is equivalent to x plus parentheses with y and z. So you can replace the parentheses accordingly. Even the same way when you multiply. I don't believe I need to spend time explaining that. You get what it is, right? Distributive theorem. So x plus and parentheses, this is equivalent to multiplying this what inside the parentheses with what outside. So x multiply with y, x multiply with z, this give you that, x multiply with y, x multiply with z will give you that. So this may be one that little someone may have a little concern about. When you add 0 to x, let's say if there is someone who doesn't know the answer all the time, if we group up with someone who may know the answer sometimes, who may not know the answer sometimes, let's say to group of 2, there is one individual who never know the answer, then the answer will be always depend on the other person who may know or may not the answer, right? So that's why when you add x with 0, it's always x. regardless of what response the other person carry, we know that he's always not contributing. And when you multiply, if there is someone who always know the answer, if there is someone who always know the answer, if you multiply, it's going to be always the answer that's coming from the person who may or may not know the answer. So if you multiply, the variable will be the answer. If you add, still the variable will be the answer. So when you add x and x dash, so it's always 1, right? So when you take a Venn diagram, sum of what allocated for x and the not allocated x is equivalent to 1, right? So if you take an exam, your score and the deduction together considered as 1 or 100%. When you multiply x dash is always 0. So as you have different type of operators, so operation precedence has been defined. The highest is given to the complement, and then to the and to the or. So as you have it here, so these are the same rules applied here. I'm not gonna spend time. Because we have so many other things that we need to pay close attention. So now here, um, uh, zero theorem that which was not in the slide before. So when you have someone who always know the answer, if you have someone who always know the answer, regardless of who his partner is, when you add those two, it's gonna be always true answer, right? If you pair up with someone who perfectly know the answer, you know, all the time, who study hard, you get perfect score all the time. But if you multiply with someone who never know the answer, you always get 0. Because if I say if both doesn't know the answer, you get 0, that's what it is. If I say that if both doesn't know the answer, you get 0, that's what it is. Even though you know the answer, if your partner doesn't know, if he's always 0, the answer remains 0. So can I get a quick um, yes or no? Everyone get what I've presented so far?
Yep.
Yep.
Yeah, good, good. So these theorems has been expanded in this way. So when you have a x multiply y plus x, so you can sum it up in this way too, right? So when you sum it up, you can bring it to a smaller value than what's represented previously. So x y x dash z plus y z, sum it up to x y and x dash multiply z. So spend a little time how this conversion can be done based on the previous theorems. I'm not going to spend time on that because our goal is not basically to spend time on the theorem, but apply those to bring the logic gates, simplify the logic gates. I'm sure you all remember this as well, De Morgan's law. This also probably have at least mentioned 1 or 2 times in the past. Not in this class, but of course in 239 and other classes. Okay, so where we need to pay our close attention is starting from here, the logic diagrams. So logic diagrams do have 3 basic kinds that we have discussed in the past. So you know the AND gates, you know the OR gates, you know the NOT gate. So AND gate only give you positive output when the both inputs A and B are positive. The OR gate will give you positive output at least if one of those inputs are positive. NOT gate will always uh, invert what you send in. If you send 0, it will convert to 1. If you send 1, it will convert to 0. So now, combination of those can generate multiple other gates. So AND with a NOT. So previously I said AND is positive or generate a 1 when both are 1. Now and generate 1 for every scenario except when both are 1, the opposite of the previous one. In the same way, XOR gate, opposite of the XOR gate, when none of those are 0, none of those are positive, you get 1. So one additional gate that not really opposite of the previous gate, but a kind of a combination. When only one input is 1, we generate the XOR gate, XOR. So AND gate is basically a, sorry, AND gate and an inverter. Together we call it a NAND gate. And the similar way, the OR gate and a inverter, you call it a NOR gate. So precedence also defined in the same way as the previous. Now, how about when you have 3 inputs? So A, B, C. So in an AND gate, even if you have 3 inputs, AND result positive only when all 3 of those are positive. Every other scenarios, the output is remain false or the 0. Keep those in mind because we're going to use it in a minute. And some of the set theorems that you probably have familiar, you may know this, intersections, and intersection is represented in the AND gate. OR gate will represent the set union, and in inverter is the set complement. Okay, now truth table have a, you can easily match what represented in a truth table using a logical diagram. So that's what we're gonna do here. So now for an example, assume you have a representation like this. So you have A, B, C. B is being inverted here and sent to an AND gate, and A is taken into an OR gate with the result of inverted B and C AND gate. The end result is A plus B, C. So now, as you see it here, based on our previous theorems, so this is written as B dash C. So now, if any one of these values becomes 0, this becomes 0. Everyone agree?
Yep.
Okay. So as you send it to the OR gate with the addition, if any one of those values is positive, this become positive. Do you agree?
Mm-hmm.
Okay. So that's the idea of representation of OR gate. When you represent AND gate, you go with the multiplication. When you do a OR gate, you do a addition. So that is actually the opposite of the previous representation, because AND is representing addition, OR is representing multiplication, but when it comes to the gate, AND is represented with the multiplication, the OR is represented with the addition.
So
Now, yeah, question?
can you go back to that last one? So say like A was 1, B was 1, and C was 1.
Say it again. A is 1.
Yep, B is 1 and C is 1.
Uh-huh.
So B would be turned into 0.
0. Then the B dash C will be 0, right? Because if
Yep.
any one of those are 0 in an AND gate, that will be 0, right?
Yep. And then,
So then this is 1. Still the end result will be 1, because
okay.
if at least 1 is 1, this will be 1.
Okay.
Right?
Yep.
So even in a larger complex algorithm, so a larger complex representation of the logical gate, see now here the A, B, C, and A and B both sent to a 2 AND gates after not making it inverted here. Then it is sent to an OR gate here, right? OR gate here, and it is sent to another AND gate and to another NOT gate. So this look little complex, right? So if we draw a truth table, this is going to be a little bit of a challenge. But see, ultimately it is simplified into a simple OR gate, simple gate representation, simple expression, right? So simple expression. So what we can do is, in order to represent all of these, we can draw a simplified design of this OR gate. Simplified design of this OR gate. Now you have like a multiple gates drawn here, but the end result is this, right? any design that generates this output will be equivalent to this. There need to be 3 inputs. So that's why we say that these are closed circuit. So what happened inside the circuit, we don't see. Kind of encapsulated program, right? So you have an encapsulated program. It doesn't matter what is inside as far as it's take ABC as an input and generate this as an output. So ABC as an input and that as an output, that is being simplified right here in this example. So now see in this example. So you have 3 inputs. You have 3 inputs. Based on the inputs, what are the outputs going to be is being represented here. What are the output being represented here? So whenever we draw the diagram, it's need to making it sure the what represented in the diagram match the previous diagram, but the circuit design can be different. Circuit design can be different. You don't need to have the same circuit design as far as it's generate the same output. We will come back to that in the example. We do have that in the bottom right here. Um, oh, come on, I missed that. Okay, so now try to compare this, okay, this design with this design. So see in this one, you have A, B, and C dash, right? C sent as a C dash. So now see in this design, A, B, and B, C dash. See, because in this one, for this AND gate, what we have sent is B, C dash, right? So this part is identical to that. So once you have that generated, so you send it to an OR gate, and somehow you ended up getting A, B plus B, C dash, A dash. See, if you see it here, it is the same. So you send it to an OR gate, and you have a coming up here, and convert it to a NOT with the AND, resulting this is equivalent to what is here. See, AB plus BC dash, right? Read this equation, read this expression, AB plus BC dash. See, this is AB plus BC dash. Everyone agree? AB and BC dash, right?
Yep.
And is representing using the OR gate. Then A, B, B, C plus, then you take A with the AND again, A with AND again, and you see the dash here, right, right above the parenthesis. So that need to invert the end result. So you take those two values, send it to an OR gate, add with the AND gate, and do a NOT. See now the same design. We have how many gates here? 1, 2, 3, 4, 5, 6. 6 gates being simplified to 4 gates, right? Do you get that?
Yep.
Okay. So as far as we can simplify the algorithm expression to a something like this, that is what we are looking for here. So how you simplify that? So you can simplify it using the simple theorems that we have discussed previously. You can apply the theorem to bring it to a smaller expression. Bring it to a smaller expression. If you can do that, then you draw ultimate logic diagram to the smaller or the tiny expression. But there are other ways to do that as well. One proposed solution is, so as far as you know the theorem, you can simplify. One other proposed solution is something called K-maps. Khan maps. So how this works, um, you don't need to remember all the theorems behind it, but I'll give you easy clues how you can draw a simple K maps. So as you see it here, so for all possibilities that you can represent using a B and A and B and C are this, right? So A can be 0 and 1, B can be B, C can be 0, 0, 0, 1, 1, 1, 1, 0, right? Right? So those are all the possibilities. When you see draw it here, see that one thing to be remembered, if you notice it here, so the order that it is being represented is little different than the regular order. 0, 0, you probably would like to see 0, 1 and 1, 0 and 1, 1, right? But instead you will see the 1, 1 here and the 1, 0 last. That is because this is the design that we're gonna make it simplified. So you do not keep gap of 2 between two representations. To do that, so you draw it in this way. So that's the way that this map representation define it is. So we follow the same to better represent the output. So now let's take an example here. So let's say if you want to represent this, so there are uh, two scenarios. The output is 1, A dash BC. A dash is A0, BC. This is 1. This is set to 1. And also A dash BC dash. A dash B is 1 and C dash this. So see, these two are represented with 1. Rest are zeros. So in K-maps, as far as you can represent that using the K-map, now all you need to do is draw a connect all possible ones with either with 1 or maybe 2 or maybe 4 set of uh, multipliers of 1 by 2s, multipliers of 1 by 2s. It has to be a group of 1 or 2 or 4. So now as I have two adjacent to each other, I can set that as a one set. I can set that as a one set. Before I tell you how you simplify it, see it here. So now these two are also appeared in a K-map. So we decide it to kept it in this order because now this and this can be set as a one set. So now as you have this set identified, how are we going to simplify? Now here, see this, in both of these ones, A remains 0, right? Everyone agree? Both of these, A remains 0.
Mm-hmm.
Right? So therefore, we simplify this as A dash, and also you will see the B also retain as 1, right? In both the scenarios, B also retain as 1. Agree?
Yep.
So therefore, this can be simplified as A dash B. We do not consider what C is because C variable in these two settings, right? So every such a group, we write a simplified version of it. Now this is equivalent to this. This is equivalent to this. Someone could argue how you can get the same from here and there. So if you notice it here, see A dash and B both appeared here, right? So you can take A dash and B out. That will sum up C plus C dash. You get what I mean? If you take A dash B and A dash B out, that will be C plus C dash. What is the value of C plus C dash?
0, right?
In a Venn diagram, if you have a one circle and the inverter of that circle, altogether it will be 1, right? That is like your exam score, and what you miss in the exam score is total is 100 or 1.
Mm-hmm.
Right? It's equal. So I can actually write it down here.
It'll be 1 or 0. So then
It would be, no, it's never going to be 0 because C plus C dash is always 1. Plus,
yeah, C
if it
C
is
could
C
be 1.
multiplied by 0, yes, what you're saying is right. If it is C multiplied by 0, it can be 1. 0.
Okay. Nick, you're the host now.
The class is mine. I'm assuming I'll be back. It's still recording, it says.
You've taken over.
Yeah.
Do you all hear me?
Yeah, we hear you now.
Yep.
Okay. So for some reason my connection got disconnected. I don't know. First time it's happened. So you all get that, right?
Yep.
Okay, good, nice. So again, this is just a one way of doing it. So any K maps that you draw, now see it here. So you may have more than 2 ones appear in a K maps, right? There may be more than 2 scenarios that hello.
Yep, we can hear you.
Okay, good. Sorry, I don't know. Was something wrong today. So now there are 2 ones. So we can draw 2 groups here. So now to better represent this, you have to have 2 sets. So now what will represent this? Can someone tell me? So A is vary between these 2, right?
Yep.
So therefore there won't be any A's in this. So that will be B and C, B,
Yep.
C, right? And here the A doesn't change, A retain 1, the B doesn't change, but C changes. So we skip C there. So therefore this will be B and C. Sorry, rather A and B, A and B. So that's why this is simplified for B, C, and AB. See, this long expression is simplified to BC plus AB. So instead of drawing a diagram, logic gate for this, now you can draw a logic gate for this. So same way, you may have more than 2, you may have 3 or more. You may have 3 or more. Even you may see some corner maps like this. But keep in mind, I'm not going to ask you to draw any K maps in your exam, as far as you can simplify it using the theorems, even though you don't remember the theorem names. As far as you can apply the simplification and generate the smaller version and draw a diagram, that's all matters. So now see it here. We have 4 values that not 4 values that adjacent to each other. So we even the corners we considered as a one set. So now in this one, you see that C doesn't change, right? C doesn't change, rather C dash that doesn't change. And also D doesn't change. That's why this is represented as C dash D. And the 4 corners is represented as B dash D dash, because if you notice it here, A is 1 here, change to 0, sorry, 0 here, change to 1, 0 here, change to 1, right? So therefore we cannot use A. How about B? So B is 0 here, B is 0 here, right? B is 0 here, B is 0 here. Therefore the B does not change. That's why we use B dash. How about D? D is 0 here, 0 here, 0 here, 0 here, right? That's why we represent it as B dash T dash. If you notice C changes from 0 to 1, 0 to 1. Everyone get that?
Yep.
Good, nice.
The C dash represents like a 0.
So C dash represent because C is retained 0 in this 2. See?
Yep. Okay.
Actually, C dash represent here this one, this group. See, the C dash is 0.
Yep.
Okay, if you get that idea, so that's what we need. But now, how are we gonna bring it to a how are you gonna bring this idea to represent it in our ALU? That's what matters, right? That's what matters, because in ALU, you don't need to draw a corner maps. You don't have those. In a logic gates, in a signal that comes into ALU, how are we gonna represent that? How are we gonna represent that? That's what matters. So now let's see example like this. Assume you have, remember our example, our accumulator and the index register, we had 16 digits, right? 16 digits. Assume you have a something with eight digits, each where start from D0 to D7, and you have three inputs. You have three inputs, right? Uh, three inputs. So you have a 8 coming in this way and 3 in this way. So now, in order to make any one of those values 1, any one of those values 1, depend on the value of these S values, we define which one going to be 1. So D0 is 1 if all S are zeros. D1 is 1 only when S0 is 1. Likewise, you have 8 different scenarios that you can generate from 3 S's that represent each one of those values, right? So we call this kind of a multiplexer. So you multiply the number of combinations that you can enter based on 3 values. So you have 8 combinations that you can make out of 3 that represent 8 different digits. 8 different digits. So now, let's say if you want to represent certain area, like say this certain area of your circuit. If your truth table want to represent certain area of a circuit, you can draw something like this to represent that. What I mean by what I mean by this. So let's say if your three inputs, if all three inputs are as expected, output need to be 1. If I want to do that, what logic gate design I should use? If I have 3 inputs, based on the value, certain value of those 3 inputs, I want to decide the output of that logic gate. What gate I should use? Of course, it's had to be an AND gate, right? If I have a 3 inputs, let's say whenever D is whenever D0, S1, S dash, so output is 1, right? Output is 1. So if I have a 4 different kind of output, then I can decide how all together all possible positive outputs, all possible positive outputs. So let me take another example from here to make things simplified here. Let's say yes, binary half adder. Okay, here half adder. So from this, that will explain it better. Let's say you want to add two numbers. Uh, Once you add two numbers, what are the four possibilities that you can experience? The four possibilities will be, if the two numbers both are 0, sum will be 0, the carry bit will be 0. If you add 0 and 1, sum will be 1, carry bit will be 0. If you add 1, 0, it will be 1 and 0. And if you add 1 and 1, it will be sum is 0 and the carry bit is 1, right? This is what the truth table for adding two numbers. We call this as a half adder. What it mean by that? So let's say your two inputs are A and B, come into a logic gate, and you may have a sum and a carry bit. Sum and a carry bit. So A and B comes here. A and B comes here. So if you notice it here, the sum will be 1 equivalent to a SOR gate. If you see this, only when 1 is 1, sum is 1. So this is the SOR gate, right? XOR. The carry bit is 1 only when both are 1. That's why the A and B, the AND gate is this. So altogether, this combination, we call it as a half adder. So why it's called as a half adder? It's not always we can do things with a half adder, because if you remember, now in our accumulator, sometimes we take the value in the accumulator and take another value from the memory address. You add those two. Not just those two, there can be some carry bit that from the previous one you need to add. You get that, everyone? Let's say you have a accumulator loaded up with 16 values. You have a another 16 values that you loaded from the memory address. When you add the first value, yes, of course, only 2 values. If there is a carry forward from the first 2 addition, which bring you to the next one, there can be 3 values that you need to add, right?
Mhm.
Right? Therefore, that cannot be accommodated with this adder, right? So that's why we call this as a half adder that can only accommodate 2 inputs. But there can be an adder like this, where you may have 3 inputs, which we call as a full adder. This is what we need for our ALU design, because now you have A and B. A and B alone not gonna survive. There can be some carry bit that's gonna bring a value from the previous one. So there can be a situation both A and B are 0 and the no carry bit. There can be value where both A and B are 0 and there can be a carry bit. And 0, 1 and with no carry bit, 0, 1 with a carry bit. So the previously 4 possibilities has been expanded to now 8 possibilities with carry bit. Everyone get that? Now, so this is what we need. So one of those will solve the issue of adding two numbers in a 2 digits in an accumulator. But that's not going to solve the complete problem of the accumulator, because it's only going to add 2 numbers. You need 16 of those. You get that? You need 16 of those. So let's say now you have A and B, right? You have A and B. You send it to the half adder. You send it to the half adder. Half adder will send that some value to another one. You will take, if there is any carry bit, you again perform that. Then you will have a sum, and again you will have a carry out 2, right? Carry out 2. So 2 half adders together will form a full adder. So now this circuit will solve the problem of adding 2 numbers. Everyone agree?
Yep.
Okay. So not only 2 numbers, also it can accommodate any carry forward coming from the previous addition, right? So now you add 2 numbers, you take the carry forward and take to the second level, and you do the same to the third level. Likewise, you can do it for 16 times. That's gonna resolve the problem of adding 16 digits together. You get the idea? You start from the rightmost 2 numbers. If there is a carry forward, you take it to the next one. You add those 3. If there is a carry forward, you take it to the next one. You add those 3. You do that so 16 times to completely sum up the accumulator. Is that clear?
Yep.
So that can be represented something like this. So now you have a one that coming up from the 0th position. So very first time you will not have a carry bit, right? You have A and B coming up. You may generate a carry bit and you will have a sum, right? If both are 0, sum will be 0. If both are 1, sum will be 0 still, right? And the carry bit will 1. If one of those are 1, sum will be 1, the carry bit will retain 0. Get that? Then that carry bit will define what is my next bit addition is. So now, regardless of what those two values, if there is a carry in, you add all those three together to perform, and there'll be a sum and carry out depend on those two values. You do that. So here we only have it for 4 values, assuming this length of the addition length of the ALU is only 4 bits, right? So if you replace this 4 times, that will do the addition for 16 bits. Is that clear?
Yeah.
Good, good. So now, do you remember that we discussed about the V bit that raised when the value is negative in the past? Remember at the very first week of the semester and even in the middle, with time to time, we talked about the V bit, right? Right? So now, as a result of this, when you do the carry out to the last, when you take the carry out and the previous one, this value, applying that to a SAW gate will give you the V bit. So probably you remember that we were thinking about calculating the V bit and the N bit and the Z bit and the C bit. So carry bit is easy, you know, carry out this represents C. The V is a SAW from this to this. I don't want to make you overly confused by uh, giving you any detail about this, but if you find time, spend a little time. If you take the last value from here and the last value from the carry out will define the sign of the number. So actually that's represented here. It says P bit if A and B are both positive and the result is negative, if A and B are both negative and the result is positive. So how that happened, I'll give you time to absorb that on your own. You don't need to overly worried about that because I'm not going to question you from anything to this level, but I'll go back and tell you to what level the questions will be on. So now with that understanding, so if you bring this idea, you can easily represent that in an ALU. You have two values that always come in as A and B, right? A and B, you take that value and take the carry bit in, apply the A and B, apply this algorithm, right? Apply this algorithm inside your ALU. Finally, you will get carry out, V, Z out, and N. So now at the beginning of the semester, we had the question how these N and Z and V and C are being calculated, right? So now we found the solution. Using the logic gate, you can represent the addition. You can represent the addition, not the half adder, but the full adder, because there can be a carry bit. So you take two values with a carry bit and do the addition and send it to the next, until you reach the 16 bit. Once you reach the 16 bit, you can decide the carry out, sorry, V and the Z and N. Z and N are easy to decide, right? V and Z, Z and N are easy to decide. If the answer is 0, or if the all are 0, so you decide Z, and N is also easy to decide. The V and C are decided based on the algorithm, basically the truth table. Okay, and even the rest, if you notice it here, so the detailed diagram of the same has been presented here. I do not want to make you overwhelmed with presenting all of those, but as far as you can get the idea up to here, that's all expected. So now one another thing, in ALU there can be 16 different instructions that can be sent to the ALU using 16 different combinations that you can present here. 16 different combinations that you can present here. So ALU have 4 bits to decide what instruction need to be applied inside the ALU. So that can be decided based on the 16 instructions that can send. Based on that, what need to be done is being decided. But again, if I roll back for your exam purpose, all I want would be, if you are given a expression if you are given an expression, you should be able to simplify it to a smaller format and draw a simplified expression for that. If you are given a this without the expression, so this is actually, this do have the answer and the solution both. If you are given a diagram like this, if I ask you to simplify it to something smaller like this, you should be able to do that. Okay, so how you do that? You have A and B here, A and B represented here, B and C dash, B and C dash represented here, addition of those two, A, B plus B, C dash, and then added it with A. So that is AND gate represented here, and the negation of that is represented here. If I ask you to draw a truth table for that, answer is right here. A, B, and B, C dash sent to a OR gate and to a NOT gate, rather NAND gate, AND gate with a negation. Is that clear? You think that you can do that? Sang, you think that you can do it? Nick, you can?
Yeah, maybe.
Okay. Yeah, I think as far as you can do that, that's all matters, but at least you need to have a brief understanding why we are doing all of those to get the binary addition worked in a ALU with the full ladder. Okay.
Okay.
Good. Good. Any other questions? I know we are almost to the time. So again, keep in mind, so your exam, I will send you a link to exam, hopefully by Sunday. So you have full day, but you only have, you can do it at any time within that day, but you only have 2 hours to complete the exam. Okay, 2 hours to complete the exam from the time
Is
you
it
start
2 hours or 3 hours?
So yeah, whatever the time range, I think it's 2 hours and 50. Is that 2 hours and 15 minutes? Is that right? The exam time slot, it says 2 hours and 15 minutes. The standard exam time slot. I can give you like 3 hours. It doesn't matter really, you know. I can give you like 3 hours. I know it's like 2 hours and 15 minutes is the time gap, the regular time allocation for the exam. I can give you 3 hours. Yes, I will do about 3 hours. So you will have 7 questions that covers everything that you have covered so far, including this, and I gave you the guarantee the question that you receive from this chapter will be only up to what I discuss here, the simplifying the truth table and the drawing a logic gate. Questions? Anything else? No? No questions?
I don't have any. So
Yeah, if you have no other question, you can sign off, and I will send you out course evaluation link soon after this class done. Make sure you take about 5-6 minutes to get it done. Okay.
all right. Thanks, Chana.
All right.
Thank you.
Take care. Bye bye.
Oh, I have a question on the assignment.
Okay, son. So whose photo is this? That's not you. So what's the question, son?
So the first question is asking for the input for the binary number.
Yes.
I'm not sure where to start on that.
Decimal in.
Is it the